So in preparing to launch the satellite, we've been doing research on alternative fuel sources, solid fuel sources. So most pulse plasma thrusters like this one actually use Teflon, which is a kind of plastic. It's an efficient and it's a fine fuel source, but it does have problems such as lifetime. After you fire the thruster over 100,000 shots, for example, the surface will char and it will be a lot harder to get better thrust values. A lot of misfiring can happen and things like that. And so what we have been experimenting with is looking into alternative fuel sources. One of them is sulfur. Now sulfur is better because it provides better thrust measurements, and it's going to hopefully get us farther faster in the solar system. And so how these work is it's pretty basic. So you've got two electrodes here. You've got the outer cathode and the inner anode right here. And what happens is a spark of electricity will come in through here and heat the fuel source with some UV light. And what happens is the atoms, the electrons inside of the atoms are excited to a point of escape, and this is called ionization. And during ionization, whatever your fuel is, you turn this into a plasma. And a plasma is the fourth state of matter, which is consisted of positively charged ions and free-moving electrons. And this is important because it is extremely responsive to an electric field, which means that you can use electromagnetic fields to direct your plasma and create thrust. And so that's what we've been doing here. Here is an example of a pulse plasma thruster right now. We have it under pressure in this vacuum. Vacuum chambers, we use them because in space, it's a low pressure environment. There are no particles. Well, there are, but very few particles. And so we need to be able to mimic that so we can get reliable data and good thrust values. So right here we have actually called an air-breathing thruster, which is different than solid fuel, as it actually uses air. It ionizes air, so nitrogen, oxygen, carbon in the atmosphere, and then uses that, makes the plasma, and then uses that plasma as a propellant. And so this guy right here is going to be going on a glider. So what we're going to be doing is taking this somewhere in eastern Washington, actually, and putting it on a large glider with a really large wingspan. I believe 9 meters is where we're at. And it's going to be unmanned, and it's going to glide around. And it's going to use the air in the atmosphere. And the reason we're doing this is we want to eventually move towards a large Martian glider. So having an unmanned vehicle actually glide around Mars doing surface monitoring and things like that. So I'm going to fire this really quick. I think it would be good if we dim the lights. Is that a possibility? 3, 2, 1, fire. All right, so that tiny flash that you saw, you can turn it on again. So that tiny flash that you saw, hopefully from back here, is the plasma. It's that blue light that we are directing. And if you could see back here, there's actually a pendulum that oscillates when the plasma hits it. And from that oscillating motion, we can actually deduce thrust measurements, which is the mechanical force that we're interested in. So, how these work. Okay. So I don't remember how far I went with explaining how this